Hello everybody. In the series Basics of Life, today we're talking about Mars and if it could be a harbor for life. Here on the title page you can see two images of Mars, one taken by a probe and one taken by a telescope, as you also may see it in a relatively good condition and good telescope on a Mars opposition. So first I'll give you a very short overview on some cornerstones of Mars. Then talk about evidence for life in the present very shortly. Then some evidence for life in the past. And then I'll shortly talk about terraforming on Mars. Mars is a relatively low mass planet. It has 10.7% of Earth's mass, with a lack of a magnetosphere and only a minor atmosphere. The pressure is about 100th of the Earth's atmospheric pressure at the max. As you can see here, the pressure varies quite a lot, and this also reminds us of the storms that Mars at times has. Despite the very thin atmospheres, the storms can be very severe and darken the whole surface for a couple of weeks or months. Mars has a stock of water, mainly ice, close to the poles and possibly underground, and it is estimated to be enough for an 11 meters layer. That sounds impressive, although in the past it used to be some 500 meters. So it lost most of the water. Then some quakes are still happening, coming mainly from one place, which is Cerberus Fossae. This is an extensional graben system that is still active. Apart from that, Mars tends to be very quiet, and the funny thing is it is InSight probe that has a meter for quakes, can also measure meteorite strikes, which happen occasionally. Because the Mars is a bit like the Moon. It's very quiet, and whatever you do on it will be felt as a small marsquake. By the way, this is where Cerberus Fossae can be found in Elysium Planitia. Then the history of Mars, the geological history. There were three main periods: the Noachian, the Hesperian, and the Amazonian. In the Noachian periods there were massive water flows and the Tarsis bulge was built. In the Hesperian, extensive lava plains formed, and in the Amazonian periods there were lava floods in certain regions, and for example the Olympus Mons was formed. It's quite a young volcano. Olympus Mons is huge, but it's a very flat volcano, so it's 21 or something kilometers high, and the base is 600 kilometers. So put it in Europe, and some of the smaller countries would almost be buried under this volcano. So when we look here at the scale, we see that most of the water happened here lots of time ago. Then some epochs can be split into early, middle and late, or early and late. But still, most of the activity happened early. Then the inner structure of Mars on first sight is quite similar to the inner structure of the Earth. It has a core, it has maybe an inner and outer core, it's not fully clear yet. It has a transition zone, it has a mantle, a middle mantle and a lithospheric mantle, and then a crust. On the second view, it's still quite different from the Earth because, for example, the core is much cooler than the Earth's core. Core is only 2000 to 2400 Kelvin. And you could think, is this any problem because the core is inside the planet? Yeah, it is, because there's no heat, less heat diffusing out from the core, which also means that the mantle is less active, and the outer part of the mantle and the crust build a lithosphere that is very thick. Already the crust is partly thick, but the lithosphere together with the upper mantle is very thick and very inactive. That's why the quakes and the volcanoes have almost ceased on Mars. Is there any evidence for life now? To say it very shortly, no. There are these handicaps that Mars has for still keeping life. It has no magnetosphere. Again, why is a magnetosphere important? Because the particles from the sun come right into the atmosphere. There's no protection, as for example on the Earth. That's bad for the atmosphere. And the atmosphere is very thin, and it clearly was a lot thicker in the past, probably about as thick as the Earth's atmosphere is now, or even thicker. Mars is geologically not very active. I told you, apart from Cerberus Fossae, it's more or less a quiet planet. Very contrary to the past, where the Valles Marineris were built and the volcanoes and everything. It lost most of its water, roughly 98%. And the ultraviolet radiation is coming through to the ground. And this has been discovered a couple of years ago. There is chlorine in the soil, which means you can't grow anything in that soil unless you treat it, basically wash it with a lot of water. That's quite a bummer for planting things on Mars. And yeah, you don't want to take the soil with you from the Earth over this 6 or something months trip to Mars, probably. Is there evidence for life in the past? That looks quite a bit better. The three ingredients, the magical three ingredients in the past have been there: water, organic molecules, and energy sources. We don't know how much of all of these three have been there, but water and energy sources were probably not a problem. Organic molecules, we don't know yet. There are some that have been found, as I will tell you. There is a meteorite that looks a bit as if it had life on it. It's a very old meteorite, and it comes from the time when Mars still had a lot of water. I will show it to you in a minute. And some minerals in stones have been found together with organic carbon. So it is not clear if the minerals were built under this organic carbon or what, but these places certainly should be looked at more closely in the future. The Java Falls rock, for example, but the one of the robots has found several spots with organic signals. So I already mentioned this, that the classic ingredients of life were there. The water is always discussed. I mean, most of Mars is dry, but here a probe just drove into some ice, which people said it's fake, but I don't think it's fake. There is some ice under the ground. The question is how much. And Mars could have been habitable earlier than the Earth. So in the beginning, it may have had some advantage because it was cooler sooner than the Earth. But of course, this turns out into the disadvantage because it's also colder now, and a lot colder than the Earth. It's also a lot smaller. So the heat can get out more quickly. Then the evidence that was looked at in the past a lot was this ALHA 84001 meteorite. In the Antarctic, there are some glaciers that are melting or actually sublimating, and the stones stay there basically for long times. And you can just collect them, look if they're meteorites, and if they're meteorites, catalog them and take them with you. And under these meteorites there was an S and C meteorite. I don't know the whole Shergatite something meteorite. And they are supposed to stem from Mars, because there's an exchange of meteorites from Mars to the Earth and from the Earth to Mars. Often they stay considerable time in space before coming down on the Earth. This one is 1.9 kilos. And people tried to find out where it comes from, and it could come from the Eos Cosma of the Valles Marineris. This is done by the orbiter probes that try to find signatures of the landscape. It is the oldest Mars meteorite, and here I give these times T1, T2. I don't know if this is official designation, but there are always 3 times involved in a meteorite. T0 would be when the meteorite is built. T1 is when it got freed from the surface of Mars. And T2 is when it came down to Earth. And this one was on the Earth already 13,000 years. But it was probably torn out of Mars 17 million years ago. And people found these structures on it that looked a bit like some bacteria on the Earth, and also have a similar size. And there are some magnetite crystals of unusual form, which of course is no proof for life, but it could show if there was life where it was. And of course the Valles Marineris is probably a good place to look for life, because there has been water in there. And there are some PHAs probably from Mars, whereas amino acids found in the stone is not clear if they come from Mars or if the stone has been contaminated. It was lying around for 13,000 years. But these aromatic hydrocarbons, polyaromatic hydrocarbons, they are almost certainly from Mars. That's quite a nice result. And especially considering that no probe has had to go to Mars because Mars kind of came to us. Then this Java Falls rock. Unfortunately, I can't tell you exactly what is to be thought of this finding, because there is this paper, it's very technical paper and quite hard to understand. This is more or less the situation where the robot drove through and where these minerals have been found, these phosphate and sulfide minerals. And there was organic carbon in mudstones along with these minerals. And this is what the stones look like. So there is some olivine and it changes between hard rock and these minerals inside sandier parts. And the deep UV laser instrument looked into the stones and found here this signal that you can find in some Mars stones, but not in the controls where the environment was not watery. So the authors say organic doesn't necessarily mean that it's made by life. That's a bit the problem, but it's a historic expression, organic chemistry, because in the past people thought that organic molecules can be made only by life, but of course it can be made in the lab, and it may also be made in special chemical environments. The question comes down to what was the environment back then, and could chemicals be built without life or not? Same thing on Venus, same problem we have on Venus with the phosphine. Because on the Earth it's basically always made by life, but on Venus we don't know if the chemistry is completely different or if there's still some life there, because the phosphine will be destroyed very quickly. Maybe I'll have to talk about Venus too sometime in the future. And the last point I wanted to mention is terraforming. And this is something I thought about already a lot back when I was a child, because this was kind of my dream, fly to Mars and terraform it, because it was clear for me already then that Mars is not too good place to live on right now. I have to warn you that many concepts are too simple. I think the way Elon Musk talks about it shows that he's not an expert enough on Martian environment, because just melting the water is not enough. I mean, you could in principle use some fission reactors and produce energy and melt the water, but the problem is it goes away quite quickly because of the ultraviolet. It will be split and the hydrogen goes out, and then the oxygen will just react with the ground and make more rusty surface. It's not as simple. So how do you get the volatiles for an atmosphere, and how do you keep the atmosphere? Volcanism would be a good solution. The problem about volcanism is that the whole planet is relatively cold, and this lithosphere I had mentioned is very thick. So even if you drill through that lithosphere, not much magma will come up. quite a hard thing to do, artificial volcanism, or you can just wait, but probably you won't see much volcanism. The only hope, more or less, is this Cerberus Fossae thing, but probably this won't make any volcanism either. Bringing much supplies from the Earth is not realistic. I mean, even if you send thousands of starships there, you can't bring the soil and the water and volatiles for the atmosphere. And the problem still stays that the magnetosphere has gone, so any atmosphere you temporarily produce is gonna leave. Could you put some additional mass on Mars? Actually, you would need a lot of mass. You can't just take a couple of planetoids and crash it to Mars and then think that Mars heats up and makes some magma on some atmosphere or something. And the problem is, where in the solar system would you find the mass? The mass of all the planetoids combined is only a small percentage of the Martian mass. So you have to go further. And there is probably more mass in the Kuiper belt, but it's hard to spiral that inward until it reaches Mars, because there are at least 4 big barriers to that, called Neptune, Uranus, Saturn, and especially Jupiter. So that's really not only science fiction, it's science fiction to bring lots of mass on Mars. So, and that's a problem that will stay with Mars. It's just too light and will lose not only the lightest gases, but also the medium light gases. So my recommendation is just forget about terraforming on Mars. I don't see any solution to that. Then a short outlook. Mars has changed a lot, unfavorably, due to its small mass, basically. The small mass makes the lack of magnetosphere because the core is cold, although part of it should still be liquid, but the fact is there is no magnetic field present. The small mass makes Mars lose any atmosphere it has, except from CO2, which is quite a heavy gas. Its past is very interesting also to understand life on Earth. How was it on Mars when the water was still flowing? Was it flowing regularly? Was it flowing in outbreaks? Was it flowing everywhere? Was it flowing more in volcano-related parts of the Mars, like close to Tarsis? This kind of thing. Then terraforming is more difficult than most people may think. And some organic minerals should be investigated on labs in the Earth, which makes sample return missions very, very important. But that's the NASA has planned such a sample return mission, but it's so complicated and so expensive that people didn't decide on it. And Rocket Lab also has a project to do sample return missions, but most likely the Chinese will just do it, while the NASA is still talking about it. That's my best guess. Although, is it worthwhile to just take any stones back, or is it better to take the stones that these robots have collected in water-rich regions? Or can you land just in a water-rich region, drill a bit and then fly back? That's an open question. And with the image of this dust devil on Mars, I would like to thank you for your attention and keep looking up, stay curious.